Hello and welcome to a digital lecture for Salt Lake Community College. This lecture will cover section 5.7 for Intro to Statistics, considering a difference of two proportions. Specifically, what we're going to talk about here is what we can do when we're using hypotheses of two proportions, and we have a null hypothesis that claims that the two proportions are equal to each other, or that the difference of the two proportions is zero. In these cases, it may actually be useful to what we call pool the estimates of the shared proportion. That means take the overall number of successes of all the groups divided by the number of observational units of all groups. Or, as shown in the formula here, p hat sub 1 times n sub 1 plus p hat sub 2 times n sub 2 divided by both n sub 1 and n sub 2 added. The reason this works, p hat sub 1 times n1 represents the number of successes in sample 1, since p hat sub 1 is the number of successes out of the sample size, n sub 1. And p hat sub 2 times n sub 2 is the number of successes, likewise, in sample 2. Overall, the reason for this is because of the null hypothesis claim. The null hypothesis is claiming that there is no difference between the two different samples. If that is actually the case, then whether I took the sample and split it up into two or more groups should be irrelevant. A success is a success. So if I had originally split the sample into men and women to try to show that there might be a difference there, i.e. the alternative hypothesis, however, the null is claiming that there is no difference, then whether I get a success for a male individual or for a female individual is no matter. I should be able to pull them all together as how many successes for all individuals. This is more of a convenience thing, so it'll be a little bit easier to use a lot of the values, for example, standard error, when calculating confidence intervals, as you'll see in the tip below. What standard error to use for a difference of two proportions? We're going to use a pooled proportion estimate, as we were talking about, for our hypothesis test when h sub 0 is that p sub 1 equals p sub 2, so the null hypothesis is that they're equal. That is, when the null hypothesis suggests that the proportions are equal, the pooled proportion estimate, which is p hat, is used to verify that the sample sizes are large enough by checking that for each of these, n sub 1 times p hat, and also n sub 1 times the complement, all of these we want to make sure that they are greater than 10. Or greater than or equal to 10. And also to estimate the standard error. That is a very convenient use for it. However, we will use separate sample proportions for confidence intervals or for the null hypothesis that suggests that the difference of the two proportions equals a value other than 0. For example, maybe p sub 1 minus p sub 2 equals 0.2, indicating that the null hypothesis claims that p sub 1 has a higher proportion than p sub 2 by 0.2. In these cases, p hat sub 1 and p hat sub 2, the two proportions from your sample, are used to verify that the samples are large enough by checking that all these cases are greater than or equal to 10, and also to estimate the standard error. Let's see an example of using this pooled proportion. The Stanford University heart transplant study randomly assigned patients to either receive a heart transplant or not. Of the 69 patients who received a transplant, 24 survived. Of the 34 patients who did not receive a transplant, 4 survived. What is the pooled proportion of patients who survived? For my transplant, then, it says here that of the 69, 24 survived. So that's my proportion that I'm going to label as p hat sub 1, 24 out of 69. And for no transplant, it should be 4 out of 34. Note that if we have that we're creating a pool proportion, that's implying that we're likely working with a null hypothesis that the proportions are equal to each other. That the proportion of those that get a transplant and those that don't get a transplant are relatively the same for those that survive. If we try to find that pool proportion, what I'm going to do, is show what it would look like if I did the formal formula, which would look something like this. 69, the sample size for the first set, times the proportion for that first set, plus 34, which is the sample size for the second set, times 4 out of 34, the proportion for the second set for no transplant, divided by both the sample sizes added together. Now, you don't necessarily need to use the full formula like this, because what we're going to see in these cases is that on top, when I do 69 times 24 out of 69, the 69s will cancel, leaving me only with 24. The same is also true with the 34 in the second set. So really, all I'm doing is adding the successes on top and the sample sizes on the bottom. 24 plus 4 divided by 69 plus 34. These add up to give me 28 out of 103, which is approximately 0.272. If you have any further questions, be sure to review the example videos or ask your instructor.